when is a real linear map from C to C is complex linear. When is a real differentiable function on a domain in the complex plane is complex differentiable. Right? A real differentiable function is complex differentiable if and only if it satisfies the Cauchy-Riemann equations. Of course, again, equivalent to saying that the real and imaginary parts have continuous first partial derivatives, again satisfying the Cauchy-Riemann equations. And then an analytic function was defined as a function which is differentiable at every point of the domain that we are looking at. Right? The simplest examples of analytic functions are the polynomials, which are analytic everywhere in the plane, so they are what are called entire functions. And then we have the rational functions, which are quotients of polynomials. These are not analytic everywhere because of the zeros of the denominator there. So except at the zeros of the denominator, a rational function is analytic everywhere in the plane. So it's again only a finite number of exceptional points, right? A polynomial has only finite number of roots. So a rational function is analytic in the whole plane minus a finite set. The most important examples of analytic functions are given by power series. Right? So we take any power series, we saw that there are essentially three possibilities. It converges only at the center. Right? If you are looking at a power series around point z0, then it converges only at z0. So this is the first possibility. This is a trivial case, not interesting. And the second case is where there is a finite positive number r such that the power series converges everywhere inside the disk of radius r with center at z0. And moreover, the convergence is absolute and uniform on every closed disk inside that. Or if you like, you can also say inside any compact subset of that disk of radius r. Of course, the third possibility is that the radius of convergence is infinite, in which case the power series converges everywhere in the plane, and that gives rise to an entire function. Of course, that comes later because we proved after that. So the first result was any power series, there is R such that the power series converges inside that disk of radius R and does not converge outside that disk. On the boundary, anything can happen. So this circle is called the circle of convergence. The radius of the circle is the radius of convergence. And the most important thing is that inside the circle of convergence, the function represented by the power series is analytic, right? Differentiable at each point of the disk, and the derivative is given by the power series again, which is got by differentiating the original power series term by term. Each term you differentiate. If you have sigma an z to the n, so the power series for f prime z is going to be sigma n an z to the n minus 1. The differentiated series, we observe that it also has the same radius of convergence as the original power series. So you can differentiate as many times as you want. And every time you get a power series, the same radius of convergence. So all those therefore represent analytic functions inside the circle of convergence. So all the derivatives also are analytic functions. Yeah, that's all I think we did. Of course, as examples, we have the most important function of all, namely the exponential function, and then the sine and cosine function defined in terms of the exponential function. So these are all entire functions which are not polynomial, so they are called transcendental entire functions. Okay? I think that's where we stop. So the task for today is to show that starting from our definition of analyticity, how to get a power series expansion for the function around each point in the domain. Right? Every analytic function has a local power series expansion. What is meant by local? In a neighborhood of each point, right? Of course, your domain can be anything, whereas your domain of convergence of any power series is a disk, right? So you can't expect a power series expansion which holds the whole domain, right? So this expansion holds only locally around each point of the domain, right? So this was what we started with, right? In the beginning, we said, in the complex case, in contrast to the real case, once you assume a single differentiability, you get the strongest form of smoothness, namely not only infinite differentiability, but actually a power series expansion. See, yesterday we saw that anything which has a power series expansion is infinitely differentiable. So having a power series expansion is stronger than infinite differentiability. In the real case, of course. In the complex case, everything is the same. Just once differentiability or infinite differentiability or power series expansion. So that's the magic of the complex plane. Okay, so now we would like to get that, what we were promising in the first lecture, that any analytic function has a local power series expansion. Okay, so towards that, so basically what we are going to do is what is called Cauchy's theory. So everything depends on the concept of a function, the integral of a function along a curve. Okay, so what is usually called as contour integrals or integrals over a path or whatever. So if you have a function which is defined in a domain and you have a curve lying in the domain, so we want to talk about the integral of that function along that curve. But what is a curve? It's a function. We will at least stick to continuity. It's a continuous curve, if you want. A continuous curve is a continuous map from a closed interval into your domain, whatever domain you are looking at. A continuous curve in omega is a continuous map from a closed interval into omega. But then for our purposes, continuous curves are not good enough. For one, we are interested in differentiability of functions. Another problem is the length of the curve, whatever it means, right? A continuous curve may have infinite length. Of course, when you think of a curve, you don't think of the function, but the image, right? Image of the function in the domain. So you might have heard of space-filling curves, for example, or piano curves. So they are kind of pathological curves, but they are nevertheless continuous curves. They have infinite length. See, there is a continuous function from the unit interval 0, 1 on to, for example, the unit square. So it fills every point of the unit square. So the length is obviously going to be infinite in that case. So we don't want to look at such curves for our purposes. So to start with, we will like curves which have finite length. These are what are called rectifiable curves. Actually, we are not going to discuss this also, but at least you should. So continuous curves. Rectifiable curves. So what is a rectifiable curve? Essentially speaking, curves whose lengths are finite. But how do you define? Mathematically, have you heard of functions of bounded variation? So a rectifiable curve is a function of bounded variation. So what does it mean? See, geometrically, if you look at a curve, how do you get the length of the curve? You can approximate the curve by polygonal lines, right? Line segments, like that. So like that, okay? So you add up the lengths of all these line segments. So as you take finer and finer polygonal arcs like that, you are going to approximate the length of the curve, right? So basically, a function of bounded variation gives you that. Supremum over the lengths of all polygonal arcs with vertices on the curve is finite, right? So that means if alpha is a curve, you'll take a partition. So this is the interval on which alpha is defined, the curve is defined. If sum over all points of subdivision here, so alpha tj minus alpha tj minus 1, look at the sum of the absolute. So this is just the length of the line segment. If this is alpha tj minus 1, this is alpha tj, this is nothing but the length of that line segment there. Okay. So what the sum represents is the sum of the lengths of all those line segments that you have drawn. The supremum over all this, but what you take supremum over what? All possible partitions, all possible polygonal arcs like that, which translates into all possible partitions of the interval. Okay, so this supremum is finite. So this is, this supremum is called the length of the curve by definition. So this is the length of the curve. But we are going to be slightly more restrictive. We are not going to consider just rectifiable curves, but slightly more conditions, smoother curves. So for example, continuously differentiable curves. Alpha is differentiable and alpha prime is continuous. But there is a problem, right? In the sense that when you say differentiable, so for example, these polygonal arcs are not differentiable. At each corner, there is a problem of differentiability. Although continuity is there, but there is a problem of differentiability. So the most suitable class of curves for our purposes, what are called piecewise continuously differentiable functions. Meaning, you have the interval, so there is a subdivision of the interval, so that on each subinterval, the function is C1. At the endpoints, I mean the points of subdivision, you may not have differentiability, right? Just like these corners here. So, the most suitable class of curves for our purposes are continuously differentiable curves. So, that's what we will do. Okay? So, all the curves that we are going to look at will be assumed to be piecewise continuously differentiable. Although, of course, much of the theory can be developed for rectifiable curves, but we need slightly more complicated proofs for various things. So, but for all our purposes, for purposes of complex analysis, this piecewise C1 will be good enough. So that's what we will stick to. Okay? So piecewise C1 curves. So all our curves will be assumed to be piecewise C1. C1, of course, means continuously differentiable. So you have a domain, you have a piecewise continuous, piecewise C1 curve in the domain. You want to integrate functions along such curves. Okay? So, of course, the integral can be defined without much problem for, say, continuous functions, for example. All our integrals that we are going to define are going to be Riemann integrals. So, no problem about integration. So, essentially, what we want to look at are what usually is written in this form. Fz dz over the curve C. So what is the meaning of this? How do you define this? Of course, C is assumed to be piecewise C1 for our purposes. So C is given by t going to something, that t. So this is piecewise C1. So of course for this, it's enough if you assume f is continuity. F is continuous, right? You don't need analyticity or anything. Suppose f is continuous on C. So C is a continuous curve in your domain omega. Okay. Of course, right now the domain is not relevant, right? You have some continuous, some curve in the plane. F is defined on that curve and continuous on that curve. So if curve is given by the function zt, so we can talk of z prime t. So if you like, what is going to be this? dzt is going to be z prime t dt, right? Z is zt, function of t. So the obvious way to define the function, the integral, is to define it as integral from a to b f of zt z prime t dt. But again, you see, uh, Z prime is defined only on, I mean, not on the whole interval, but there are some points where it's not defined, but that doesn't matter as far as the integral is concerned, right? Even if your function has finite number of discontinuities, it's going to be Riemann integrable. Or if you like, so you can split the curve into parts, on each of which you receive one, right? And then add up, integral over the whole thing is by definition integral over this plus integral over this plus integral over that, and so on, right? So either way, you can view this integral. So this is the Riemann integral, okay? When you think of a curve geometrically, the picture, you need what is called an orientation. You're going this way or coming this way, right? So that has to be kept in mind, especially for closed curves. Uh, this way or that way. But usually the anti-clockwise orientation is taken to be a positive orientation. The other one is the negative orientation. Let's note that if you have a curve C, so you can define a curve, the opposite curve. If C goes this way, minus C will go this way. But how do you define the function? So reflect everything about the origin. So minus C is going to be defined on minus B minus A into your domain by T going to minus ZT. No, sorry. Z of minus T. If T belongs to AB, if and only if minus T belongs to this. Okay? So if if C starts at A, not A, whatever, point alpha here, ends at B, beta, minus C will start at beta and end at A. Of course, the point Z of A is called the initial point. Z of B is called the terminal point or whatever. Of C. And then integral over minus C of f z dz is going to be minus f z dz. That's from the definition. Of course, if you have that the initial point is same as the final point, then you get what is called a closed curve or a loop. Of course, one uses the term loop more when you discuss homotopy or something of that kind, fundamental groups and so on. So it's a closed curve. It's essentially the most important fact of the whole business, whole of complex analysis, is that f is analytic and C is a closed curve, and I mean, this is not as simple as that, but essentially, under suitable conditions on the domain, conditions on the curve, and so on, integral of an analytic function around a closed curve is 0. This is the basic theorem. It's called Cauchy's theorem. But just stated this way, it's completely false. Okay, unless you impose suitable conditions on the curve or on the domain, and so on. Right. This is Cauchy's theorem. With suitable conditions, that is important, right? It's not a global statement without any qualification, right? You need really strong conditions on the curve or on the domain. So this is the most basic theorem. So we will come to that later, but let's now at least evaluate some of the simpler integrals, examples for integrating functions along contours. Okay. Suppose, so mostly we will be dealing with only closed contours. Okay. Suppose C is closed. So general is a kind of blanket assumption. What about Z dz? So essentially, you see, so what is the proof for this? Or even constant functions, if you are integrating, where do you get 0? Along closed curves, of course. Okay. Of course, if you look at the definition, in this case it is trivial. Z is a constant, Z prime is going to be 0, so whole thing is going to be 0. But, so this is 0. What about this? So let me ask a slightly more general question. Suppose your f is such that there is a function g whose derivative is f. There is a g such that g prime is f. Then what can you say about so this is going to be can you tell me, at least guess what the answer is going to be? Just look at the Riemann integral. Forget all these curves and everything. Right? If you have a differentiable function f prime on an interval ab, okay, what is a to b integral f prime dt, f prime t dt? Huh? f of b minus f of a. So can you guess the answer in this case? F of the function evaluated at the end point of the curve in general. You don't have to take a closed curve for that. F evaluated at the end point minus f evaluated at the initial point. F of zb minus f of za. If the curve is closed, it's going to be 0. Right? But that needs a proof, whatever you said. See whether you can prove that. So this is going to be I don't know, we might have used some other, instead of using z itself, we might have called it something gamma or something. Okay, but it doesn't matter. Is alpha and there's beta, let's say. So if C is closed, so this is 0. So if a function is the derivative of some other function, then integral along a closed curve is 0. Right? In this case, you say that f has a primitive. G is called a primitive of. Primitive means a function whose derivative is the given function. So a function which has a primitive, the integral is 0 along any closed curve. So that needs a proof, right? That's not an obvious thing from the definition, but it's not difficult either. Okay. So look at this case, for instance, now. The function z, it has a primitive, right? Obviously, namely, what is the primitive for z? Z square by 2. If you differentiate z square by 2, you are going to get z. So this is going to be 0. So more generally, powers of n. Which powers of z will have this property? Let's, for simplicity, let's take a circle, right, around 0. Say mod z r. Center 0 and so in other words, what I'm asking is which powers of z are, have primitives? All powers, all positive powers. What about negative powers? 1 over z, for example, does it have a primitive? Log z is a tricky thing. Complex logarithms. So a priori, we'll not talk about log z right now. But 1 over z square, for example, if you take, do you have something whose derivative is 1 over z square? And go back to your school. How do you integrate? What do you get if you integrate 1 over x square? You're going to get something, right? Minus x cubed by 3 or whatever, right? Z square is, 1 over z square is the derivative of something, right? So all powers except minus 1, right? As long as n is not minus 1, what happens to this power minus 1? That is an important case for us for various purposes. So let us take, for example, where C is the circle. Circle with center Z0 and radius R, let's say. So let us call it C Z0 R. Okay. So what is this? You have to Z prime T dt. So Z prime now is R e power it and then I. Z minus Z naught is REIT. Right? So what do you get? This 2 pi I is a very important number in complex analysis. It will appear everywhere, not only in complex analysis, even in Fourier analysis, it is going to appear everywhere. So what is the picture now? Here, this is the. So this is Z naught. This is your C, CR, whatever it is, C Z naught R. If you look at, if you take a smaller disk, of course, R is arbitrary, for any R, independent of R, this one is. But if you take a domain like this, you take two circles, the same center at Z0, the function 1 over Z minus Z0 is analytic in this. In this domain. All right, if you take this as your omega, so except, in fact, it's analytic everywhere outside this any disk around 0, right? Around Z0. So this actually, therefore, is a closed contour in a domain where the function is analytic, right? Fz is analytic in omega, C is a closed contour in omega, but still integral of Fz dz is non-zero. So you already see that this is not universally true, right? Without conditions on the domain or on the curve or anything, right? So that has to come always with qualifications. So you have an analytic function, a closed contour, the integral around that analytic the closed contour is non-zero for this analytic function. So it's a very important thing to observe. Simple thing, but. So remember this integral. This will be needed again and again in future. One of the chief objectives is to prove such a thing under suitable conditions. We'll actually prove many results of that kind with various conditions, right? But we start with a very simple situation where this holds. But the most general form of that Cauchy's theorem, we'll postpone it to a later part of the course. We'll use a simple form of Cauchy's theorem to, first of all, to obtain whatever we said already, get a local power series expansion for analytic functions. So this is what is called you can call it as Cauchy's theorem for a triangle. Or a rectangle you can take, doesn't matter. But a triangle in some ways is simpler. This is also referred to as I mentioned Gusa yesterday. So he was the one who showed that in the definition of analyticity, assuming the continuity of the derivative is not needed, is superfluous. So for that, proof actually will use this. Actually, Gusa's lemma was the original Gusa lemma was for rectangles, but we'll do it for triangles because we have some advantages when you look at triangles in contrast to rectangles. So what does this say? When you take your closed curve to a triangle, the integral is 0 for any analytic function. Basically, that's what it is. Suppose f is analytic in omega, T is a triangle in omega such that, so when you say a triangle, it's only the boundary now we are talking about, but we want the interior of the triangle also to be contained in omega such that the triangular region bounded by, we can give some name there, it will be useful, bounded by T is also contained in omega. In other words, the triangle and also the interior are subsets of omega. Then actually probably it's better stated, starting with this and then saying that for every function which is analytic on omega. This is true for any function which is analytic in omega. Okay, doesn't matter. But before we go into the proof of this, let us look at some things about integrals that we need. This will be needed repeatedly, so we need a bound for this integral. F is a continuous function, so C is a compact set, right? It's an image of an interval, closed interval. So absolute value of F has a maximum on the curve C. So this is bounded by maximum on C of mod F. So we'll use this notation, convenient. Maximum of mod Fz as Z varies over C times the length of C. Oh, probably I didn't mention I mentioned rectifiable curves, curves of finite length and so on. But we are looking at C1, piecewise C1 curves. These have finite length, right? In fact, the length is given by is finite. Any continuously differentiable function is a function of bounded variation. Basically, that's the with our assumptions on the curves, this length is finite. So bound for the function on the curve times the length of the curve. That's the bound for the integral. Okay, so forget the domain, look at the triangle. This is your T. So the strategy is to subdivide the triangle into smaller triangles. So to be specific, let us take the midpoints of all the sides and form a triangle. Right? So joining the midpoints of the sides of T we get four triangles. Let's call them as Tj. So just mod Z prime T, right? That will give you the length of the image curve there. Anyway, so so you get four triangles now. So, right, you are going to integrate like this. You can also integrate along each smaller triangle. You are going to integrate like this, and then you are going to integrate like that, like that. So when you add up, what will you get? For example, if you take this one of these things, so this is a side of two of the triangles. When you integrate along this triangle, it's going to be oriented this way. When you integrate along this triangle, this is going to be oriented the other way. Right? So integration along this plus integration along this will give you 0. One is negative of the other. So in other words, if you look at what are you going to get? So all these sides of the inner triangle will cancel out, and you will end up with integral along this plus integral along this. This will give you the integral of the whole thing, so on. So you will just end up with integral over T fz dz. So the integral that we want to evaluate is this sum of these four integrals. When you take absolute value, this is going to be less than or equal to sum of the absolute values of this, right? is what we are going to get. If you take, so what is the relation between this and each one of this? Want to compare? Of course, in absolute values. If each of, there are 4 terms, remember, okay? So if each of them is less than 1/4 of this, then the whole thing is going to be less than this. You can't have strict inequality in all the terms. So at least one of this will have to be greater than or equal to 1/4 of this. So for some j, one of these triangles. Okay? So choose such a triangle and let's say call it such a Tj as T sub 1, let us say. What do you do now? Start with T1 and repeat the whole thing. Take this as T1, divide, you'll have 4 triangles again. Integral over T1 will be equal to sum of the integral overs all this. And in the same way, you will get integral over T1 is greater than or equal to 1/4 of integral of one of those smaller ones. So call that as T2, and so on. Right? Also observe something about the lengths of these triangles. Length of T and length of these smaller triangles. What is the relation? We have taken the midpoints, so each of them is half the length of the size of the bigger triangle. So length is half the original triangle. Note that length of T1 is half of length of T. So proceed. So start with T1. And repeat the argument. To get a triangle T2 with and of course the length What about the triangular regions themselves? Of course, each is contained in the previous one. Okay. Note also that with obvious notation, the triangular region. So in each case, you have the triangular region. If this is T1, you have this closed triangle there. So they decrease, right? This is the original triangle region. Right? Of course, now This delta 1 will be the triangular region bounded by T1 and so on, the obvious notation. So what do you get therefore? You get a sequence of triangles this way. So we get, so right now only so much, then we get a sequence Tn of triangles such that, okay, so delta n plus 1 contains delta n, length of Tn is half, or Tn plus 1 is half the length of Tn, and integral mod fz dz is equal to 1/4